Close your eyes for a moment if you'd like. You don't need them for this. Tonight isn't about watching anything. It's about listening, slowly, while your mind lets go of the day and drifts somewhere far quieter. Tonight, we're going to talk about algebra. I know, that word alone might have made your shoulders tense a little. For most of us, algebra wasn't something we chose. It was handed to us in a classroom, on a whiteboard, in the middle of a school day we didn't ask for. Solve for x. Simplify the expression. Show your work. It felt cold, mechanical, something to survive rather than something to enjoy. But what if I told you that algebra didn't start that way at all? What if I told you that algebra began not as a set of rules, but as a story? A very long, very human story, stretched across thousands of years, dozens of civilizations, and countless quiet minds who were simply trying to make sense of the world around them. There were no x's in the beginning, no y's, no plus signs, no neat little equations lined up on a page. For most of human history, algebra didn't look like mathematics at all. It looked like language. It looked like patience. It looked like people, sitting in candlelight or firelight, working through a problem one careful sentence at a time. So tonight, we're not going to rush through formulas. We're going to walk, slowly, through the long and winding history of an idea that started with grain and land and debts, and slowly, over centuries, grew into one of the most powerful tools the human mind has ever created. Let yourself sink into the pillow. Let your breathing slow down. There's nowhere you need to be, and nothing here you need to remember. Just let the story carry you. Let's start with a simple question. What is algebra, really? Not the version you remember from school, but the true, original idea underneath it. At its heart, algebra is about relationships. It's about understanding how one thing changes when another thing changes. It's about taking something unknown, something hidden, and finding a path toward knowing it. Think about that for a second. An unknown quantity, something you cannot see directly, but something you can reason your way toward. That idea alone is almost poetic when you sit with it. Long before anyone used the letter X, people were already doing this. They were solving for the unknown in their own quiet way, using nothing but words and careful thought. Imagine you needed to describe an equation without any symbols at all. No x, no equal sign, none of the shorthand we take for granted today. You'd have to say something like, the unknown quantity, when increased by 5, becomes 8. Every single time you wanted to describe a relationship like that, you'd have to write it out, sentence by sentence, in full. It sounds exhausting from where we sit now. And yet, for thousands of years, that was simply how mathematics was done. People built entire systems of thought, solved remarkably complex problems, all without a single mathematical symbol to lean on. They carried it all in careful language and careful memory. There's something almost soothing about that, isn't there? No shortcuts, no rushing, just slow, deliberate thinking, one word at a time, the same way we're moving through this story right now. Before algebra had a name, before it had symbols, before it even had a country to call its own, it began quietly in the daily life of ordinary people. Not in a university, not in a laboratory, in fields, in marketplaces, in the record-keeping of everyday problems that needed everyday answers. Somewhere, someone needed to divide a piece of land fairly between their children. Somewhere else, someone needed to calculate how much grain would be needed to survive a long winter. Somewhere else again, a merchant needed to work out interest on a loan, a problem that, believe it or not, is remarkably similar to problems still taught in classrooms today. These weren't abstract puzzles dreamed up for fun. They were real. They mattered. A wrong answer could mean a family went hungry, or a debt spiraled out of control, or land was divided unfairly and unjustly. Mathematics, in its earliest form, wasn't a subject, it was survival. And it's worth pausing here, in the quiet, to really sit with that idea. The origins of algebra are not found in abstract genius sitting alone with a stroke of inspiration. They're found in necessity, in ordinary people doing their best to solve ordinary problems, slowly discovering that certain patterns kept repeating, certain methods kept working, and somewhere in that repetition, something remarkable began to take shape. Over the coming parts of this story, we're going to travel together. Slowly, gently, the way sleep itself moves. We'll drift toward ancient riverbanks, toward candlelit rooms filled with careful calculations, toward scholars working by lamplight in libraries that no longer exist. We'll meet civilizations that never spoke to each other directly, and yet somehow arrived at strikingly similar ideas, each one adding a small piece to a puzzle none of them could see the whole of. We'll meet people who solved equations using nothing but geometry and careful reasoning. We'll meet people who gave algebra its very name, in a language and a culture far from the classrooms most of us grew up in. We'll meet minds who worked in secrecy, protecting their discoveries the way a person might protect a treasured secret. And we'll meet others who worked in the open, sharing their knowledge freely, believing that understanding belonged to everyone. None of it happened quickly. None of it happened in isolation. It happened slowly, the way most meaningful things do. One civilization would build a foundation. Centuries later, another would come along and build upon it, refine it, expand it, without ever fully realizing how far their ideas would eventually travel. That's the shape of this story. Not a straight line, but a long, slow river, winding through deserts and river valleys, through quiet libraries and quiet minds, patiently gathering more and more understanding as it moved forward through time. So for now, let that be enough, just the beginning of a beginning, a quiet acknowledgement that somewhere, thousands of years ago, in a place very different from wherever you are right now, someone sat down with a problem they didn't yet know how to solve. And in trying to solve it, without realizing it, they took the very first step of a journey that would eventually reach all the way to you, lying here, drifting slowly toward sleep. In the next part of our story, we'll travel to one of the very first places this journey truly begins. A land between two rivers, where clay tablets still hold the fingerprints of scribes who lived and worked and calculated nearly 4,000 years ago. Let your mind rest here for a moment. We'll continue soon, slowly, the way all good stories should. Let's travel back now, far back, past your grandparents, past every name in any history book you were ever handed in school. We're going back nearly 4,000 years to a stretch of land nestled between two great rivers, the Tigris and the Euphrates, in what is now modern-day Iraq. This was Babylon. Picture it slowly, the way a dream forms. Warm, dry air, fields of barley swaying gently near the riverbanks. Mud brick homes, narrow streets, the quiet hum of a civilization that had already been thriving for centuries. Babylon wasn't a primitive place. It was organized, sophisticated, and deeply practical. And it's here, in this ancient land, that our story of algebra truly begins to take its first real shape. The Babylonians faced problems that feel almost familiar, even now. How do you divide a piece of farmland fairly between several children? How do you calculate interest owed on a loan of silver or grain? How much grain does a household need to set aside to survive until the next harvest? These weren't puzzles for entertainment. They were the quiet, practical mathematics of daily survival. And so, slowly, over generations, Babylonian scribes developed methods to solve these problems. Not with symbols, not with an equals sign, with careful, methodical language, written in wedge-shaped marks pressed into soft clay with a reed stylus. This writing system is called cuneiform, and remarkably, thousands of these clay tablets have survived, buried safely in the earth for thousands of years, waiting patiently to be uncovered. Imagine that for a moment. A scribe, sitting cross-legged on a woven mat, pressing careful marks into damp clay by the light of an oil lamp. Around them, the sounds of a city slowly settling into evening, and in their hands, a problem not so different from the ones we still teach today. Somewhere on that tablet, in words rather than symbols, is a version of what we would now call a quadratic equation. It's remarkable, really, how advanced their thinking was. The Babylonians weren't simply doing basic arithmetic. They were solving equations that involved unknown quantities multiplied by themselves, what we would today call squaring a number. They developed step-by-step methods, almost like recipes, for finding these unknown values. Take this number, add this, divide this in half, square the result. Their language for it was different, but the underlying logic mirrors what we still teach students today, thousands of years later. What's especially striking is that they had no concept of a negative number. Their entire mathematical world existed in the realm of the positive, the tangible, the countable. And yet, working entirely within that limitation, they still managed to develop procedures for solving what we would now call quadratic and even certain cubic equations. Methods built not from abstract theory, but from patient trial, careful observation, and centuries of refinement passed down from teacher to student. Let that sink in slowly. There was no symbol for X, no plus sign drifting across a page, just sentence after sentence, written out in full, describing a process. Take the unknown, multiply it by itself, add a known quantity. The result equals this. It's almost meditative to imagine, isn't it? A slower, more deliberate kind of thinking. No shortcuts, just steady, careful reasoning, one step following naturally from the one before it. The scribes who did this work were not ordinary citizens. They were highly trained specialists, educated for years in dedicated schools, often attached to temples or palaces. Mathematics, in Babylon, wasn't a subject taught broadly to the public. It was a specialized skill, much like reading and writing itself, reserved for those whose job it was to manage the practical affairs of a growing, complex society. Taxes, trade, land division, construction, astronomy even, since the movement of stars and planets mattered deeply to Babylonian life and religion. And this is part of what makes the story so quietly beautiful. Algebra, in its earliest form, wasn't born from idle curiosity. It was born from responsibility, from the need to keep a society functioning smoothly, from the quiet, unglamorous work of scribes solving real problems for real people, tablet after tablet, year after year. Their careful marks slowly building towards something far larger than any of them could have imagined. Some of these tablets, remarkably, contain what look almost like teaching examples, practice problems meant to train the next generation of scribes. Imagine a young student, still learning their craft, working through the exact same kind of problem a scribe centuries before them had once solved. A quiet thread of knowledge passed hand to hand, tablet to tablet, across generations who never met each other, but were somehow still connected through the shared language of mathematics. It's easy, lying here now, to imagine the warmth of that ancient evening, the soft scratch of a stylus against clay, the particular satisfaction of watching a problem slowly unravel into an answer. There was no rush in this work, no pressure of a ticking clock or a looming deadline, just patience, and the quiet confidence that comes from following a method that has worked, again and again, for as long as anyone could remember. The Babylonians never called what they were doing algebra. That word wouldn't exist for many more centuries, born in a different land, in a different language entirely. But the seed was here, planted quietly in damp clay beside two ancient rivers nearly 4,000 years ago. And slowly, as trade routes stretched further, as ideas began to travel along with silk and spices and grain, this quiet Babylonian knowledge would begin, ever so gently, to drift outward, toward other river valleys, toward other civilizations, each one about to add their own quiet piece to this long, unfolding story. Rest here for a while, if you'd like. Let the image settle. Warm clay, careful hands, an ancient evening slowly deepening into night. In the next part of our journey, we'll follow the story a little further toward another great river and another civilization who found their own patient way of solving for the unknown. Let the Babylonian evening fade now, gently, like a candle burning low. We're going to drift somewhere new, somewhere warmer, drier, following the long, winding path of another great river. This time, we're traveling to ancient Egypt and the slow, life-giving waters of the Nile. Picture it, golden light stretching across the water at dusk, reeds swaying quietly at the riverbank. In the distance, the low silhouette of structures that would stand for thousands of years after everyone who built them had long since passed. Egypt, like Babylon, was a civilization built around a river, and like Babylon, its people faced the same quiet, practical questions that mathematics has always tried to answer. How much grain is needed to feed a household through the season? How should land be measured and divided after the Nile's yearly flood reshaped the fields? How many loaves of bread should be baked, and how should payment be fairly divided among workers? These were not abstract questions. They shaped whether families ate, whether taxes were paid fairly, whether an entire kingdom continued to function smoothly season after season. Much of what we know about Egyptian mathematics comes from a single, remarkable document, now known as the Rind Papyrus. Picture a long scroll of papyrus, carefully preserved, covered in neat rows of hieratic script, the everyday cursive writing of ancient Egypt. This scroll dates back roughly to 1650 years before the Common Era, and remarkably, the scribe who copied it tells us he was working from an even older document, one that reached back centuries earlier still. Isn't that a comforting thought, in its own quiet way? Even to the scribe writing this papyrus, mathematics already felt ancient, already felt like something inherited, passed down carefully from teachers whose names had long since been forgotten. A slow, patient chain of knowledge, stretching backward and forward through time. Inside this papyrus are dozens of practical problems, worked through with careful, methodical explanations. Many of them wrestle with a very particular kind of challenge, problems involving an unknown quantity, something the Egyptians simply called the heap. A heap, increased by its own seventh part, equals 19. Find the heap. There's something gentle about that word, isn't there? The heap. Not X, not a cold, abstract symbol, just a heap. A quiet stand-in for something unknown, waiting patiently to be discovered. To solve problems like this, Egyptian scribes developed a method historians now call the method of false position. It's a beautifully intuitive idea, even now. You begin by guessing an answer, almost certainly the wrong one. Then you carefully observe how far off your guess turned out to be. And using that gap, that quiet measure of error, you adjust your original guess until it settles precisely into the correct answer. Take a moment to sit with how patient that approach really is. No shortcuts, no formula to simply plug numbers into. Just careful trial, careful observation, and careful correction, repeated slowly until the unknown finally reveals itself. It mirrors, in a strange and quiet way, the kind of patience sleep itself asks of us. You don't force it, you simply keep adjusting, gently, until you arrive exactly where you need to be. Egyptian mathematics also had a particular fascination with fractions, though not in the way we use them today. Rather than writing a fraction like 3/5, Egyptian scribes broke nearly every fraction down into a sum of what are called unit fractions, fractions with a numerator of 1. 3/5 might be expressed as 1/2 plus 1/10. It sounds unusual to us now, almost unnecessarily complicated, but within their system, it worked beautifully, consistently, for centuries. This wasn't mathematics for its own sake. It was deeply tied to daily Egyptian life. Architects used these methods to calculate the slope and dimensions of monuments that still stand today, their proportions worked out using nothing but careful arithmetic and geometric reasoning. Officials used similar methods to calculate taxes owed based on the height of the Nile's flooding each year, a measurement that directly determined how fertile the coming season's harvest would be. Picture for a moment an Egyptian official standing at the riverbank, watching the water slowly rise against a carved stone measure called a nilometer. The height of that water would soon become a number. That number would soon become a calculation. And that calculation would soon determine how much every household across the land would owe in taxes that year. Mathematics, quiet and unassuming, sitting at the very center of an entire civilization's well-being. There's a soothing kind of symmetry in comparing Egypt to Babylon, two great river civilizations separated by considerable distance with almost certainly limited direct contact between their scholars. And yet, independently, each culture arrived at strikingly similar ideas. Each one developed its own patient methods for solving for an unknown quantity. Each one built its mathematics not from abstract curiosity, but from the practical, grounded needs of daily life. It suggests something quietly beautiful about the human mind itself, that faced with similar problems, in similar circumstances, separated by rivers and deserts and thousands of miles, people will often arrive, slowly and independently, at remarkably similar solutions. As if certain patterns of thought are simply waiting to be discovered whenever a mind is patient enough and curious enough to go looking for them. The Egyptians never called their heap an unknown variable. They never called their careful methods algebra. That word, and the more formal mathematics that would come to define it, was still many centuries away, waiting quietly in the future. But here, in the warm evening light along the Nile, another quiet piece of the puzzle was being carefully set into place. Let your breathing slow a little further now. Picture the river, calm and golden in the fading light. In the next part of our story, we'll leave the riverbanks behind for a while and travel toward a very different kind of algebra altogether, one built not from numbers and heaps, but from shapes and lines and the quiet elegance of geometry itself. Let the Nile fade quietly behind us now. We're drifting somewhere new again, across the sea this time, toward the rocky coastlines and marble courtyards of ancient Greece. The air feels different here, cooler, sharper, filled with the quiet hum of philosophers debating beneath olive trees. This is a civilization that approached mathematics in a way unlike anything we've encountered so far in our story. Where Babylon and Egypt built their mathematics around practical, everyday problems, grain, land, taxes, interest, the Greeks approached mathematics with a very different kind of curiosity. For many Greek thinkers, mathematics wasn't primarily a tool for solving daily problems. It was a pathway toward understanding truth itself, toward certainty, toward something eternal and unchanging, hidden beneath the surface of the physical world. And this shift in thinking changed everything about how algebra developed, at least for a while. The Greeks, and in particular a mathematician named Euclid, approached what we would now call algebraic problems through geometry. Instead of thinking of an unknown quantity as an abstract number waiting to be found, they thought of it as a length, a line, a shape whose dimensions could be carefully constructed, measured, and reasoned through using nothing but a straight edge and a compass. Picture it slowly. Instead of writing an equation on a page filled with numbers and symbols, imagine a Greek mathematician drawing careful lines in sand or on a wax tablet, constructing rectangles and squares to represent the relationships between quantities. If a problem involved multiplying an unknown value by itself, they wouldn't think of it as squaring a number the way we do today. They would picture, quite literally, the area of a square, its sides representing the unknown quantity itself. This approach is often called geometric algebra, and it's a beautifully different way of thinking about the same underlying ideas we've been following since Babylon. The problems were similar in spirit. still about unknown quantities, still about relationships between different values. But the language, the very way of picturing these problems, had shifted entirely from words and numbers toward shapes and space. There's something quietly meditative about this approach, if you allow yourself to sit with it. Rather than manipulating symbols abstractly, Greek mathematicians were, in a sense, thinking with their hands and their eyes. Drawing, constructing, watching a solution slowly take physical shape in front of them, line by careful line. Euclid's great work, a collection of books known as The Elements, gathered together centuries of accumulated geometric knowledge into one enormous, carefully structured whole. Within certain sections of this work, hidden inside what looks, at first glance, like pure geometry, are proofs that are functionally equivalent to solving what we would now call quadratic equations. The unknowns are lengths, the equations are areas, but the underlying logic, the careful step-by-step reasoning toward an unknown value, remains remarkably familiar. Why did the Greeks approach things this way? Part of the answer lies in a quiet crisis that shook Greek mathematical thinking to its core. At some point, Greek mathematicians discovered the existence of what we now call irrational numbers, numbers that cannot be expressed as a simple ratio of two whole numbers. The most famous example involves the diagonal of a simple square. No matter how precisely you try to express that diagonal as a fraction, it simply refuses to resolve neatly. For a culture deeply invested in the idea of mathematical certainty, this discovery was unsettling. It suggested that numbers, in the way they had been understood, might not be capable of fully describing reality. And so, in response, many Greek mathematicians leaned further into geometry. Lines and shapes, unlike certain numbers, could still be constructed and reasoned about with total certainty, even when the numbers underlying them refused to behave neatly. It's a quiet reminder that mathematics itself has never been a fixed, unchanging thing. Even thousands of years ago, thoughtful minds were wrestling with uncertainty, adjusting their entire way of thinking in response to a single, unsettling discovery. Much like we sometimes have to adjust our own thinking, slowly and carefully, when something we once assumed to be simple turns out to be more complicated than we expected. Not every Greek mathematician worked this way, of course. Centuries later, closer to the end of the ancient Greek era, a mathematician named Diophantus would begin moving algebra in an entirely new direction, one far closer to the algebra we recognize today. But we'll come to him gently in the next part of our story. For now, let's simply rest here a while longer in the quiet world of geometric reasoning. There's a particular kind of stillness in this Greek approach to algebra. No rushing toward a numerical answer, no frantic search for a formula. Just patient construction, line by line, shape by shape, until a solution reveals itself naturally, almost as though it had been hiding there in the geometry all along, simply waiting to be uncovered by a patient enough mind. Imagine, for a moment, a mathematician working late in the evening, a small oil lamp casting a soft glow across a wax tablet. Slowly, carefully, they draw a square, then a rectangle beside it. They study the relationship between the two shapes, turning the problem over in their mind the way you might turn over a familiar thought just before falling asleep. And slowly, patiently, an answer begins to take shape, not as a number scrawled quickly on a page, but as a shape, quiet and certain, resting there in front of them. This is the quiet gift the Greeks gave to our story. Not a faster way of doing algebra, but a deeper way of seeing it. A reminder that behind every equation, behind every unknown quantity waiting to be found, there is often a shape, a relationship, a structure quietly holding everything together. Let your mind rest here for a moment, among the marble courtyards and quiet geometric reasoning of ancient Greece. In the next part of our journey, we'll meet a mathematician who began to shift algebra away from pure geometry and towards something that finally starts to resemble the algebra so many of us remember from our own school days. Stay with me a little longer in Greece, though we're going to move forward in time now, quietly, the way years slip by unnoticed when you're half asleep. We're traveling to the city of Alexandria, centuries after Euclid, to meet a mathematician whose life remains, even now, wrapped in a gentle kind of mystery. His name was Diophantus, and historians sometimes call him the father of algebra. Though, as we've already seen, that title is more of a gentle honor than a strict truth. Algebra, as we know, had already been growing quietly for thousands of years before he was born, in Babylon, in Egypt, in the geometric reasoning of earlier Greek thinkers. But Diophantus did something quietly important. He began to nudge algebra away from geometry and back toward numbers themselves. We don't know a great deal about his life. No detailed biography survives, no portrait, no collection of personal letters. What we do know comes almost entirely from a single, rather charming source, a riddle written about him after his death, preserved in a collection of Greek mathematical puzzles. And there's something quietly fitting about that, isn't there? A mathematician whose own life story survives to us only in the form of a math problem. The riddle describes his life in fractions. It tells us that his childhood lasted 1/6 of his life. His beard grew after 1/12 more. He married after 1/7 more passed. 5 years later, a son was born. But the son, sadly, lived only half as long as his father. And Diophantus, grieving deeply, lived 4 more years after his son's death before passing away himself. If you sit with that riddle patiently, working through the fractions the way Diophantus himself might have taught you to, you eventually arrive at an answer. He lived to the age of 84. Whether this riddle is entirely accurate or simply a loving tribute crafted by someone who admired his work, we may never fully know. But it captures something quietly beautiful about how his contemporaries chose to remember him. Not through ordinary words, but through the very language of mathematics he had spent his life refining. Diophantus's major surviving work is a text called the Arithmetica, originally believed to span 13 books, though only a handful have survived the passage of time. Within these pages, something quietly revolutionary begins to happen. Diophantus starts using a kind of shorthand notation, abbreviations and symbols to represent unknown quantities and operations, rather than writing everything out in long, flowing sentences the way earlier mathematicians had done. It wasn't yet the algebra we would recognize today. His symbols were closer to abbreviations than the clean, universal notation we use now. But it was a meaningful, quiet shift, a movement away from pure prose and towards something more compact, more efficient, more focused purely on the relationships between quantities rather than the words used to describe them. Historians sometimes describe this stage of algebra's development as syncopated algebra, a middle point between the fully written-out language of Babylon and Egypt and the fully symbolic algebra that wouldn't fully emerge for many more centuries. It's a lovely word for it, syncopated, almost musical, as though mathematics itself was slowly finding its own quiet rhythm. The problems within the Arithmetica are also strikingly different from what came before. Rather than focusing on practical, everyday concerns like land division or grain storage, many of Diophantus's problems are more abstract, more purely mathematical. He was particularly fascinated by problems involving whole number solutions, equations where the answer needed to be a neat, whole quantity rather than a fraction or an irrational value. This particular kind of problem, equations that require whole number solutions, is now known, quietly and permanently, as a Diophantine equation, named in his honor. Even now, more than 1,500 years after his death, mathematicians continue to study Diophantine equations, some of which remain unsolved to this day. There's something almost comforting in that thought, a quiet mathematical curiosity, first written down in Alexandria so long ago, still gently occupying the minds of mathematicians working late into the night. All these centuries later, Diophantus's influence would go on to travel much further than he could have ever imagined during his own lifetime. Centuries later, his work would be studied carefully by mathematicians in the Islamic world, who would build upon his ideas and push algebra even further forward. And centuries after that, in the 17th century, a French mathematician named Pierre de Fermat would famously scribble a note in the margin of his own copy of the Arithmetica, claiming to have found a beautiful proof for a certain kind of equation, a proof that, according to him, simply wouldn't fit in the margin. That small note would go on to become one of the most famous unsolved problems in the entire history of mathematics, remaining unproven for over 350 years until it was finally resolved in 1994. All of it, in a quiet, roundabout way, tracing its roots back to a single mathematician working carefully in Alexandria, centuries and centuries before. There's something deeply calming about following a thread like this. A single idea, planted quietly by one patient mind, drifting forward through history, touched and gently reshaped by other patient minds, generation after generation, long after the person who first wrote it down has been gone. Diophantus never could have known his careful notation and his quiet fascination with whole number solutions would still be occupying minds nearly 2,000 years later. And yet, here we are. Let your thoughts settle here for a moment. In the quiet Alexandrian evening, imagining Diophantus bent carefully over a scroll, testing solutions, refining his abbreviated notation, slowly nudging mathematics one gentle step closer to the algebra we know today. In the next part of our story, we'll leave the Mediterranean behind entirely and travel east toward ancient India, where mathematicians were quietly developing ideas that would prove just as essential to algebra's long, unfolding history. Let Alexandria fade quietly into the distance now. We're traveling east, further than we've gone so far in this story, toward the warm plains and river valleys of ancient India. The air feels different again here, filled with the sound of temple bells somewhere in the distance, and the quiet rustle of palm leaves used, remarkably, as writing material in a time long before paper found its way to this part of the world. India's contribution to the story of algebra is often quietly overlooked, tucked into the margins of textbooks, when in truth it belongs somewhere near the very center of this entire journey. Some of the most important ideas underlying all of modern mathematics, ideas we now take entirely for granted, were first carefully worked out by Indian mathematicians, centuries before they ever reached Europe. Let's begin with a mathematician named Aryabhata, who lived and worked around the year 500 of the Common Era. Picture him surrounded by students, patiently explaining astronomical calculations, the movements of planets, the timing of eclipses, all of it deeply tied to mathematics in a way that feels, even now, remarkably elegant. Aryabhata developed methods for solving what we would now recognize as linear and quadratic equations, and his work on trigonometry would go on to influence mathematicians for centuries after his death. But it's another Indian mathematician, born roughly a century later, who made perhaps the single most quietly revolutionary contribution to this entire story. His name was Brahmagupta, and among his many achievements, he was among the very first mathematicians in recorded history to treat zero not simply as an absence, a placeholder, but as a true number in its own right. A number you could add, subtract, multiply, a number with its own quiet, legitimate place within the world of mathematics. Take a moment to really sit with how significant that idea is. So much of mathematics as we know it today, algebra especially, depends entirely on zero behaving as a proper number. Without it, so many of the equations and methods we now take for granted simply couldn't function the way they do. And yet, for a long stretch of human history, many civilizations either lacked a symbol for zero entirely or treated it as nothing more than an empty placeholder, a gap rather than a genuine quantity. Brahmagupta changed that, quietly and carefully, in a text called the Brahma Sfuta Siddhanta, written around the year 628. Within its pages, he laid out precise rules for how zero should behave in arithmetic. Adding zero to a number leaves it unchanged. Subtracting a number from itself produces zero. He even ventured into the far more difficult, almost philosophically uncomfortable territory of dividing by zero, an idea mathematicians would continue wrestling with for centuries afterward. And Brahmagupta didn't stop there. He was also among the first mathematicians to work carefully and systematically with negative numbers, describing them using the language of debts, while positive numbers represented fortunes or assets. A debt combined with a fortune of the same size cancels out to nothing, he explained, patient and precise, in a way that feels remarkably intuitive even now, especially if you've ever quietly balanced a budget late at night, watching debts and assets cancel each other out on a page. This willingness to accept negative numbers as legitimate mathematical quantities was, quietly, a significant leap forward. The Babylonians hadn't used them, neither had the Egyptians, nor most of the Greeks, who remained deeply uncomfortable with any quantity that couldn't be represented as a physical length or area. But Brahmagupta, working from a different tradition entirely, saw no reason to exclude them. A number was a number, whether it represented a fortune or a debt. Indian mathematicians also developed increasingly sophisticated methods for solving quadratic equations, methods that allowed for both positive and negative solutions, something earlier civilizations had often overlooked or dismissed entirely, since a negative length or a negative area simply didn't make intuitive sense within a purely geometric framework. By stepping away from geometry and thinking instead in terms of pure numerical relationships, Indian mathematicians were able to see solutions that had remained quietly hidden from other traditions. There's a gentle irony worth pausing on here. The numeral system most of the world uses today, the very digits you're picturing right now, 9 gentle little symbols plus a circle for 0, did not originate in Europe, despite often being called Arabic numerals. They originated here, in India, refined over centuries by mathematicians like Aryabhata and Brahmagupta, before eventually traveling west, first into the Islamic world and only much later into Europe itself, carried slowly along ancient trade routes by merchants and scholars who recognized just how useful this elegant system truly was. Picture for a moment an Indian mathematician working quietly by lamplight, carefully writing out these new numerals on a palm leaf manuscript, completely unaware that the small circle they were using to represent 0 and the simple curved digits beside it would eventually travel across deserts and oceans, reshaping mathematics for every future civilization that encountered them. It's a quiet, patient kind of legacy, not loud, not dramatic, just steady, careful thinking, passed gently forward through time. By the time these ideas began reaching the Islamic world, and eventually Europe, algebra had already absorbed contributions from Babylon, Egypt, Greece, and India, each civilization adding its own quiet, essential piece. Numbers and unknown quantities, and now, finally, the willingness to work comfortably with 0 and negative values as well. The foundation was slowly, patiently coming together. Let your thoughts rest here a while, imagining that small circle for 0, quietly waiting on a palm leaf manuscript, about to begin its own long journey westward. In the next part of our story, we're going to follow that very journey toward a city filled with scholars and libraries, where algebra would finally, quietly, be given the very name we still use for it today. Let the palm leaves of India settle quietly behind us now. We're traveling west again, toward a city that, at the time, was quite possibly the greatest center of learning anywhere in the world. This is Baghdad, sometime around the early 9th century, during a remarkable era historians now call the Islamic Golden Age. Picture it slowly. Wide streets lined with libraries. Scholars from Persia, from Greece, from India, from across the known world, gathering together in a single extraordinary institution known as the House of Wisdom. Manuscripts arriving from distant lands, carefully translated into Arabic, studied, discussed, and quietly built upon by some of the brightest minds of the era. This wasn't simply a library, It was something closer to a vast, patient conversation between civilizations that had never before had the chance to speak so directly with one another. And it's here, in this quiet, candlelit world of scholars and translated manuscripts, that we finally meet the mathematician who would give algebra the very name we still use today. His name was Muhammad ibn Musa al-Khwarizmi, and if this entire story has a single central figure, it's quietly him. Al-Khwarizmi worked at the House of Wisdom, where he had access to an extraordinary range of mathematical knowledge, Babylonian methods, Greek geometry, and, crucially, the numeral system and algebraic techniques developed in India, including that quietly revolutionary concept of zero. Rather than simply preserving this knowledge, he did something remarkable. He wove it together, patiently, into a single, unified, systematic approach to solving equations. Around the year 820, Al-Khwarizmi wrote a book with a long and rather beautiful title, which translates roughly to The Compendious Book on Calculation by Completion and Balancing. Within its pages, he introduced two key operations for solving equations, operations he called Algebra and Al-Muqabala. Algebra referred to the process of moving a quantity from one side of an equation to the other in order to eliminate a negative term, restoring balance, almost as though you were gently completing something that had been left incomplete. Al-Muqabala referred to the process of balancing an equation by canceling matching terms on either side. Take a slow breath here, because this is the quiet moment our story has been building toward. That word, algebra, would eventually travel across languages, across centuries, gently reshaped by translators and travelers until it finally arrived, softened and adapted, as the very word we still use today. Algebra. Isn't that a lovely thing to rest on for a moment? A word we've all heard 1,000 times, in classrooms, on homework assignments, in casual conversation, actually means something quietly beautiful in its original context. Restoration. Completion. The careful process of making something whole again. Not a cold mechanical procedure at all, but something closer to gently repairing balance where it had been lost. Al-Khwarizmi's approach to algebra was also quietly groundbreaking in another important way. Where earlier mathematicians had often solved individual problems using methods tailored to that specific situation, Al-Khwarizmi worked to develop general methods, step-by-step procedures that could be applied to entire categories of equations, regardless of the specific numbers involved. He carefully worked through 6 standard types of equations, showing, patiently and systematically, exactly how to solve each one. This might sound like a small distinction, but it represents a profound shift in how mathematics was being approached. Rather than simply solving a particular problem, Al-Khwarizmi was building something closer to a toolkit, a reliable, repeatable method that could be taught, learned, and applied by others, long after he himself was gone. It's the quiet difference between solving a single puzzle and teaching someone how to solve every puzzle of a certain shape for the rest of their life. Interestingly, Al-Khwarizmi still relied heavily on geometric reasoning to justify why his methods worked, drawing on that older Greek tradition we explored earlier in our story, even while presenting his solutions in a more systematic, procedural way. It was, in a sense, a quiet bridge between the geometric algebra of the Greeks and the more abstract, symbolic algebra that would eventually follow many centuries later. There's a particular kind of stillness worth imagining here. Al-Khwarizmi, working quietly by lamplight in the House of Wisdom, surrounded by manuscripts written in 6 different languages, patiently drawing together threads of knowledge that had developed independently, thousands of miles apart, over thousands of years. Babylonian methods for solving equations, Indian numerals and the concept of zero, Greek geometric reasoning, all of it quietly gathered together, refined, and organized into something new, something more powerful than any single civilization had managed entirely on its own. His name, too, would go on to leave a quiet mark on mathematical language. When his works were later translated into Latin and studied throughout medieval Europe, his name, Al-Khwarizmi, was gradually transformed by translators into the Latin word algorithmy. And from that quiet mistranslation, centuries later, we get the word algorithm, a term now used constantly throughout mathematics and computer science, describing exactly the kind of careful, step-by-step, repeatable process he pioneered all those centuries ago. Sit with that for a moment, drifting slowly towards sleep. Two words in constant daily use across the modern world, algebra and algorithm, both quietly tracing their origins back to this single scholar, working carefully in a candlelit library in 9th century Baghdad. Two ideas born from the same patient mind, still shaping the world more than 1,000 years later, still present, quietly, in your phone, your computer, your daily life, whether you ever think about it or not. Let your thoughts settle here for now, among the quiet halls of the House of Wisdom, imagining manuscripts gently unrolled beneath lamplight, ancient knowledge slowly being gathered, translated, and made whole again. This is where our story pauses for tonight. In the part still ahead, we'll follow this knowledge as it continues traveling westward into medieval Europe, through dramatic rivalries, secret formulas, and the slow, patient birth of the very symbols we still use in algebra today. Let's stay a little longer in Baghdad, in that same quiet, candlelit world we drifted through before. We left Al-Khwarizmi surrounded by manuscripts, his great book on restoring and balancing freshly written. But there's more to his story worth resting on tonight, more that helped shape not just what algebra was called, but how algebra actually worked, step by patient step. Picture him seated on a low cushion, a wooden writing board across his lap, scrolls stacked neatly beside him. Al-Khwarizmi wasn't simply interested in solving one clever problem after another. He wanted something far more useful than that. He wanted a method. A reliable, repeatable set of steps that anyone, a merchant, a surveyor, a student, could follow to solve an entire category of problems, without needing a flash of genius each time. This was, in its own quiet way, a revolutionary shift in how people thought about mathematics. Before him, solving an equation often felt like solving a riddle, a clever trick discovered for one particular situation. Al-Khwarizmi wanted to strip away the cleverness and replace it with something calmer and more dependable. A procedure, something you could teach, something you could trust, the same way you trust that a recipe, followed carefully, will produce the same result every single time. He organized equations into 6 basic types, based on how squares, roots, and plane numbers related to one another. Squares equal to roots. Squares equal to numbers. Roots equal to numbers. And then 3 more, slightly more complex, combining all 3 elements together. At the time, this felt necessary because negative numbers were still treated with real suspicion. You couldn't simply move a term across an equation and let it turn negative the way we casually do today. Every equation had to be carefully rearranged so that everything stayed comfortably positive. This is where his 2 now famous operations come in again. Gently, one more time. Algebra, restoring balance by moving a subtracted quantity to the other side, turning it from something missing into something present. Al-Muqabala, balancing an equation by quietly canceling matching terms that appeared on both sides. Together, these 2 operations let Al-Khwarizmi take a messy, complicated expression and slowly, patiently, simplify it down into one of his 6 clean, standard forms. And here's where the story becomes especially soothing to sit with. Once an equation was reduced to one of these standard shapes, Al-Khwarizmi didn't just present a numerical answer. He proved why the method worked, using geometry, drawing quiet squares and rectangles the way earlier Greek mathematicians once had, showing that his procedure wasn't some arbitrary trick, but something grounded, something you could see, something you could trust with your own eyes as well as your own reasoning. Imagine for a moment a young student sitting beside him, watching him draw a square on a wax tablet to represent an unknown quantity multiplied by itself. watching him extend that square gently with a rectangle to represent an added term, watching the whole shape slowly transform piece by piece until the answer sat there quietly, visible, undeniable, resting calmly in the geometry itself. There's something deeply calming about mathematics explained this way, isn't there? Not a rule handed down without explanation, but a truth you can watch unfold, slowly, right in front of you. Al-Khwarizmi's work reached far beyond equations too. He also wrote extensively on arithmetic, carefully explaining the Hindu numeral system, including that quiet, revolutionary little symbol for zero we met earlier in our story in ancient India. Through his writing, this elegant number system slowly began spreading throughout the Islamic world, and eventually, centuries later, into Europe as well, gradually replacing older, clumsier systems of counting that had lingered for centuries beforehand. He also contributed meaningfully to geography and astronomy, helping compile more accurate maps and calculating the movement of celestial bodies with newfound precision. It's worth pausing on that for a moment. In his own time, Al-Khwarizmi wasn't simply remembered as an algebra specialist. He was a broader kind of scholar entirely, someone whose careful, patient thinking touched nearly every field of study available to him. Mathematics for him wasn't an isolated subject. It was a quiet tool for understanding the entire world more clearly. What's especially worth resting on tonight is how deeply collaborative this entire era truly was. Al-Khwarizmi worked at the House of Wisdom alongside other scholars, translators, and astronomers, many of whom were quietly building on ideas borrowed from Greek, Persian, and Indian sources, blending them together into something new. Knowledge, in this particular moment of history, moved fluidly across cultures and languages, carried gently from one patient mind to another, refined a little more with each careful hand it passed through. His book on algebra would go on to be translated into Latin centuries later, becoming one of the primary textbooks used throughout medieval European universities. Students who had never heard of Baghdad, who knew nothing of the House of Wisdom, would nonetheless learn algebra directly from his careful, systematic methods, his 6 standard equations, his patient geometric proofs, quietly reshaping how an entire continent would come to think about mathematics. There's a gentle stillness worth holding on to here as we prepare to drift further along in our story. A single scholar, working carefully in a candlelit room nearly 1,200 years ago, developing a method so clear, so patient, so carefully explained, that it would still be shaping classrooms on an entirely different continent hundreds of years later. Nothing about his work was rushed. Nothing about it was flashy. It was simply careful, patient, and true. One small step building quietly upon the next. Let your thoughts settle here a while longer, imagining that same quiet room, scrolls gently unrolled, a wax tablet resting nearby with a square drawn carefully upon it. In the next part of our journey, we'll follow this knowledge as it finally begins crossing into medieval Europe, carried gently along trade routes and translated manuscripts toward a young mathematician in Italy who would help introduce an entire continent to numbers it had never truly used before. Let Baghdad fade quietly behind us now, the way a warm room fades when you finally step out into cool evening air. We're traveling west again, across deserts and seas, toward medieval Europe, a place that, for a long while, had quietly fallen behind the mathematical brilliance flourishing elsewhere in the world. Picture Europe in this era, slowly, gently, without judgment. Narrow cobblestone streets, candlelit monasteries where monks carefully copied manuscripts by hand. Trade ships drifting along the Mediterranean coastline, carrying spices, cloth, and quietly, almost invisibly, ideas as well. For centuries, much of Europe had continued using Roman numerals, a system that, while useful for simple counting, made even basic arithmetic like multiplication and division remarkably slow and cumbersome. Try for a moment to imagine multiplying 2 large numbers using only Roman numerals. No neat columns, no simple carrying of digits, just a slow, careful, often confusing process, prone to error, requiring considerable skill even for a trained merchant. It's the kind of quiet inefficiency that goes unnoticed for generations, simply because nobody yet knows a better way exists. And this is where our story gently turns toward a young man named Leonardo of Pisa, a name history would later come to know more fondly as Fibonacci. Picture him as a boy, traveling with his father, an Italian merchant and diplomat stationed in a North African trading port. There, surrounded by the bustling commerce of the Mediterranean world, young Leonardo was introduced to something that would quietly change the course of European mathematics forever. The Hindu-Arabic numeral system. The very same elegant digits, including that patient little symbol for zero, that had traveled slowly westward from India. Through the careful work of scholars like Al-Khwarizmi, Leonardo was captivated. Where Roman numerals felt rigid and cumbersome, this new system felt fluid, efficient, almost effortless by comparison. Numbers could be written in simple columns. Calculations that once took considerable time and training could now be worked through with quiet, straightforward ease. He spent years traveling further through the Mediterranean, studying with Arab mathematicians, quietly absorbing methods that had been refined and perfected over centuries in the Islamic world. In the year 1202, Leonardo returned to Italy and wrote a book called Liber Abaci, which translates gently to the Book of Calculation. Within its pages, he carefully laid out the Hindu-Arabic numeral system for a European audience, many of whom had never encountered anything like it before. He didn't simply present the numerals abstractly either. He filled the book with practical examples, merchants calculating profits, currency conversions, and yes, that now famous problem involving the breeding of rabbits, a problem that would quietly give rise to the sequence of numbers that still bears his name today. Picture the slow, patient reception this book must have received. Merchants, accountants, and scholars cautiously testing this unfamiliar new system, comparing it against the numerals they had used their entire lives. Some resisted, understandably wary of change. In certain regions, the new numerals were even briefly banned, out of concern that the unfamiliar symbols might make fraud easier to commit, since a simple zero could apparently be altered more easily than the sturdy strokes of a Roman numeral. But slowly, gently, over the course of generations, practicality won out. Merchants using the new system could calculate more quickly, more accurately, and with considerably less effort than their competitors still relying on the old ways. And little by little, quietly, the Hindu-Arabic numerals began spreading across Europe, carried not by decree or force, but simply by their own patient usefulness. Leonardo's book also carried forward algebraic methods rooted in the work of Al-Khwarizmi and other Islamic mathematicians who came after him, gently introducing European readers to techniques for solving linear and quadratic equations, techniques dressed now in the more efficient language of these new numerals. It's worth resting on how quietly essential this moment truly was. Algebra itself hadn't changed dramatically yet, but the tools used to express it, the numerals themselves, had just taken an enormous, calming step forward. There's a lovely kind of stillness in imagining this slow transition. No dramatic announcement, no single moment where all of Europe suddenly adopted these new numbers. Just decade after decade of quiet, gradual adoption. One merchant, one monastery, one university at a time. Each new adopter passing the knowledge gently forward to the next. By the time several more generations had passed, European universities were slowly beginning to establish themselves as genuine centers of learning, translating not only Leonardo's work, but earlier manuscripts as well, including, eventually, careful Latin translations of Al-Khwarizmi's own writing. Algebra, patiently carried across centuries and civilizations, from Babylon to Egypt, Greece to India, Baghdad to Pisa, was finally beginning to settle into European soil, ready to grow into something new entirely. It's worth noting too, gently, that this entire journey we've been following together was never really a single, isolated path. It was closer to a slow river delta, many quiet streams of knowledge branching and rejoining. Mathematicians in different lands, unaware of each other, yet somehow, patiently, contributing to the very same unfolding story. By the time algebra reached medieval Europe, it was already the product of countless careful minds, spread across thousands of years and thousands of miles. Let your thoughts rest here for a while, imagining Leonardo quietly writing by candlelight, carefully explaining these new numerals to a continent not yet sure it wanted them. In the next part of our story, we'll move forward a few more centuries, into Renaissance Italy, where algebra was about to take an unexpectedly dramatic turn, involving secrecy, rivalry, and a quiet, desperate race to solve a problem that had remained unsolved for thousands of years. Let's move forward now, gently, a few more centuries, toward Renaissance Italy. The air here feels different again, filled with the quiet ambition of a continent slowly rediscovering art, science, and mathematics all at once. Cities like Venice, Florence, and Bologna were bustling with scholars, merchants, and, in this particular case, a surprisingly intense rivalry over a mathematical problem that had puzzled thinkers since the days of Babylon. That problem was the cubic equation, an equation involving an unknown quantity multiplied by itself 3 times over. While methods for solving quadratic equations involving a quantity squared had existed in various forms for thousands of years, all the way back to those Babylonian scribes we met earlier in our story, the cubic equation had remained stubbornly, quietly unsolved. Nobody had yet found a general method, a reliable formula that could solve every cubic equation the way earlier mathematicians had learned to solve quadratics. In 16th century Italy, mathematical knowledge wasn't always something scholars shared freely. It's worth pausing here to notice how different this feels from the collaborative spirit we found earlier in Baghdad's House of Wisdom. In Renaissance Italy, mathematics had, in certain circles, become something closer to a competitive sport. Universities would sometimes hire mathematicians based on their public performance in mathematical duels. Contests where 2 scholars would exchange problems, and whoever solved more of them correctly and swiftly would win prestige, students, and a coveted teaching position. Picture the tension of that world for a moment. Mathematical knowledge wasn't simply studied quietly for its own sake. It was currency. A secret formula, kept carefully hidden, could mean the difference between a comfortable academic position and a life of quiet struggle. And it's within this tense, competitive atmosphere that our story's central rivalry slowly begins to unfold. A mathematician named Scipione del Ferro is believed to have been the first to discover a method for solving a particular type of cubic equation, sometime in the early 16th century. But true to the secretive spirit of the time, he never published his discovery. Instead, he quietly shared it only with a small circle of trusted students, ensuring his own advantage remained safely protected. It's a small, telling detail about this era, isn't it? A discovery capable of reshaping mathematics, deliberately kept in the shadows. After Del Ferro's death, one of his students, hoping to secure his own reputation, used this secret formula to challenge another mathematician to a public contest. That challenger's name was Niccolò Fontana, more commonly remembered by his nickname, Tartaglia, meaning the stammerer, a name he carried due to a childhood injury that had permanently affected his speech. Tartaglia, working independently and under considerable pressure, managed to rediscover the method for solving cubic equations entirely on his own, just in time to defeat his opponent in their public mathematical contest. Picture that quiet, private tension. Late nights, working by candlelight, racing against a looming public deadline, aware that his entire reputation rested on solving a problem that had remained unsolved for thousands of years. He succeeded, and true to the customs of the time, he too kept his method carefully secret, sharing it with almost no one. This is where a mathematician named Girolamo Cardano enters our story. Cardano was a fascinating, complicated figure, a physician, an astrologer, and a passionate mathematician, eager to publish a comprehensive book gathering together the algebraic knowledge of his time. Learning that Tartaglia had solved the cubic equation, Cardano wrote to him repeatedly, gently, patiently, asking to be shown the method. Tartaglia resisted for a long while, understandably protective of a discovery that had cost him so much effort and anxiety to uncover. But eventually, after considerable persuasion, and reportedly after Cardano swore a solemn oath never to reveal the method publicly, Tartaglia relented, sharing his solution, encoded carefully within a cryptic poem, a common practice at the time for protecting mathematical secrets from being easily understood by outsiders. For a while, quiet as a held breath, Cardano kept his promise. But then, sometime later, Cardano and his own student, a talented young mathematician named Lodovico Ferrari, learned of Del Ferro's earlier, independent discovery, the very same method Tartaglia had built upon. Reasoning that Tartaglia was therefore not the true original discoverer, Cardano felt released from his oath, and in 1545, he published the method openly in a book called Ars Magna, or The Great Art, along with considerable further mathematical work of his own, including a method his student Ferrari had developed for solving even more complex fourth-degree equations. Tartaglia, understandably, was furious. What followed was a long, bitter public dispute, an exchange of accusations and mathematical challenges that stretched on for years, drawing in other mathematicians of the era, each side defending their reputation with as much determination as they had once brought to solving the equation itself. It's a strange human note to sit with, isn't it, gently, as your thoughts begin drifting toward sleep. Even here, in the quiet, patient history of algebra, human emotion, pride, and rivalry played just as significant a role as pure mathematical reasoning. And yet, despite all the tension and secrecy, something remarkable happened. The cubic equation, unsolved for thousands of years, stretching all the way back to those careful Babylonian scribes, was finally, openly, permanently solved and shared with the wider mathematical world through Cardano's published work. Whatever the personal conflicts involved, the knowledge itself was now free, available to any future mathematician willing to study it carefully. There's a quiet lesson resting gently within this entire episode. Mathematics, throughout history, has never existed in some pure, untouched vacuum, separate from human ambition, pride, or rivalry. It has always been created by people, with all their complicated emotions intact, working sometimes in cooperation and sometimes, as we've just seen, in quiet, simmering competition. Let your thoughts settle here a while, imagining candlelit studies filled with cryptic poems and carefully guarded secrets, mathematicians racing quietly against each other through the night. In the next part of our story, algebra is about to undergo one final, essential transformation, the slow, patient birth of the very symbols, the x's and the plus signs, that we still rely on today. Let the tension of that old rivalry settle now, gently, like dust after a long day. We're moving forward again, a little further into the story, toward a quiet but essential transformation, one that would finally give algebra the visual language most of us associate with it today. Letters, symbols, the neat, compact equations that once felt so cold to us back at the very beginning of this journey. Up until this point in our story, remember, algebra had always been expressed in ways that feel, by comparison, remarkably slow. The Babylonians and Egyptians wrote everything out in careful, patient sentences. Diophantus introduced a kind of shorthand, abbreviations that saved a little time, but still felt closer to language than pure notation. Al-Khwarizmi, Fibonacci, even Cardano and Tartaglia, all of them were still, in their own ways, describing mathematical relationships largely through written words, occasionally supported by simple abbreviations. That was about to change, quietly, patiently, through the careful work of a French mathematician named François Viet, working in the late 16th century. Picture him, a lawyer by profession, working on mathematics largely in his spare time, driven by a quiet fascination with finding more elegant, more general ways of expressing mathematical relationships. Viet introduced something that feels almost obvious to us now, precisely because it worked so well that it became permanent. He began using letters to represent not just unknown quantities, the way earlier mathematicians occasionally had, but also known quantities as well. Vowels for unknowns, consonants for knowns, a distinction that feels quaint today, but at the time represented a genuinely new way of thinking about equations. This might sound like a small, technical detail, but sit with it for a moment, slowly, the way you might turn over a comforting thought before sleep. For the first time, mathematicians could work with general relationships, entire families of equations, rather than solving one specific numerical problem after another. An equation could now describe a whole category of situations at once, a quiet, powerful kind of abstraction that hadn't fully existed before. Viet called this new approach the analytic art, and while his particular notation wouldn't be the version that survived into the algebra we use today, he planted an essential seed. Mathematics, he demonstrated, patiently and clearly, didn't need to be tied to specific numbers at all. It could operate on pure relationships, expressed through carefully chosen symbols, applicable to endless different situations. From here, our story drifts gently toward another quiet, transformative mind. A French philosopher and mathematician named René Descartes, working in the early 17th century. Descartes is remembered for many things: his philosophy, his famous meditation on thought and existence. But tonight, we're resting on his quiet contributions to mathematics itself. Descartes refined the notation Viet had introduced into something remarkably close to what we still use today. He began using lowercase letters near the end of the alphabet, X, Y, and Z, to represent unknown quantities, and lowercase letters near the beginning, A, B, and C, to represent known, fixed quantities. He also introduced the small, raised numbers we now call exponents, a simple, elegant way of writing x multiplied by itself, rather than spelling it out awkwardly each time. Picture for a moment how calming this small shift truly was. An equation that once required an entire, careful sentence to express could now be written quietly, compactly, in a single, clean line. The unknown quantity, once called the heap by Egyptian scribes, once called the thing in medieval European texts, had finally settled into the simple, familiar shape of a lowercase x, resting gently at the center of an equation, waiting patiently to be solved. Descartes also made another profound contribution to our story, one that gently merged algebra with the geometric thinking of the ancient Greeks we explored earlier. He developed what we now call the Cartesian coordinate system, a simple grid built from two perpendicular lines, allowing any algebraic equation to be drawn quietly and precisely as a shape, a curve, a line, resting calmly on a page. This was, in its own gentle way, a reunion. Remember how the Greeks had once approached algebra almost entirely through geometry, lines and shapes standing in for numbers. And remember how Diophantus, and later Al-Khwarizmi, had gradually shifted algebra back toward pure numbers and symbols. Descartes, centuries later, found a quiet way to bring both approaches back together, showing that an equation and a shape were, in a deep sense, simply two different ways of describing the very same underlying relationship. Picture an equation quietly transforming into a smooth curve, drifting gracefully across a grid, each point along that curve representing a solution to the very same relationship once written out, painstakingly, in ancient Babylonian sentences thousands of years earlier. It's a beautiful thing to rest your thoughts on, isn't it? This quiet reunion of number and shape, patiently rebuilt across so many centuries. With Viet's careful groundwork and Descartes' elegant refinements, algebra finally arrived at something close to the visual language most of us grew up with. Letters for knowns and unknowns, simple symbols for addition, subtraction, and multiplication, most of which were also being quietly standardized by other mathematicians around this same era. Equations that could be written swiftly, read clearly, and applied broadly to problems far beyond the specific numbers that had originally inspired them. It's worth resting for a moment on just how long this transformation actually took. Nearly 3,000 years passed between those first careful Babylonian clay tablets and the clean, symbolic notation Descartes was quietly refining. 3,000 years of patient, incremental thought, each civilization adding its own small, careful piece, until finally, algebra found the visual shape it still wears today. Let your thoughts rest here for a while, imagining a quiet grid, a smooth curve drifting gently across it. An equation finally settled into the calm, familiar shape of letters and symbols. In the next part of our story, we'll follow algebra a little further still, toward a mathematician whose work would help expand these new symbols into an entirely new, even more powerful branch of mathematics. Let the quiet grid of Descartes fade gently now, its smooth curves settling into the soft dark behind us. We're moving forward once more, toward the latter half of the 17th century, a time when the careful symbolic language algebra had only just finished acquiring was about to be stretched, gently and profoundly, into something even larger. This part of our story unfolds across two quiet, separate studies, one in England, one in Germany, belonging to two remarkable minds who, without direct collaboration, were about to arrive independently at a strikingly similar breakthrough. Their names were Isaac Newton and Gottfried Wilhelm Leibniz, and together, in their own separate, careful ways, they would help develop what we now call calculus, an entirely new branch of mathematics built directly upon the algebraic foundation so many earlier civilizations had spent thousands of years quietly constructing. Picture Newton first, working largely in solitude at his family's countryside estate, during a period when Cambridge University had temporarily closed due to an outbreak of plague sweeping through England. Away from the noise and structure of university life, alone with his thoughts for months at a time, Newton found space to think slowly, patiently, deeply, about problems that had quietly puzzled mathematicians for generations. How do you precisely describe motion that is constantly changing? How do you calculate the exact area beneath a curve, rather than simply approximating it? These questions might sound abstract, drifting gently past you as you settle further into sleep, but they touch something remarkably practical. How fast is an object moving at a single, precise instant, when speed itself is constantly shifting? How do you calculate the changing trajectory of a planet or the curving path of a thrown object using nothing but careful reasoning and the algebraic tools already available? Newton's answer involved what he called fluxions, a method for understanding how quantities change continuously over time. Using the symbolic algebra so carefully developed by Viette and Descartes before him, letters representing unknown, shifting quantities, Newton found a way to describe not just a fixed relationship between numbers, but the very rate at which those numbers were changing, moment by careful moment. Meanwhile, quietly, separately, in Germany, Gottfried Leibniz was wrestling with remarkably similar questions, arriving, through his own careful reasoning, at strikingly similar conclusions. Leibniz, however, approached the problem with a slightly different notation, one focused on infinitesimally small changes, tiny, careful differences between one moment and the next, accumulated patiently to reveal a larger, continuous pattern. It's a quietly beautiful echo of something we've encountered earlier in our story, isn't it? Remember the Babylonians and Egyptians, arriving independently at similar mathematical ideas, separated by rivers and deserts, with little to no direct contact between them. Centuries later, here it happens again, this time between Newton and Leibniz, two minds separated by a channel of sea rather than a desert, each quietly discovering, through their own patient reasoning, a version of the very same profound idea. Unfortunately, unlike the earlier civilizations we've explored, whose contributions blended gently together across centuries without conflict, Newton and Leibniz's discovery led to a long, uncomfortable dispute over who deserved credit for developing calculus first. Their supporters, rather than their own quiet studies, carried much of this argument forward, dividing much of Europe's mathematical community for years along national lines. It's a gentle reminder, again, that mathematics has never existed apart from the very human tendencies toward pride and rivalry we witnessed earlier with Tartaglia and Cardano. But setting the dispute aside for now, letting it drift quietly into the background, what matters most for our story is this. Calculus, this new, expanded branch of mathematics, could not have existed without the patient algebraic foundation built by every civilization we've journeyed through together tonight. The careful equation solving of Babylon, the geometric reasoning of Greece, the symbolic shorthand of Diophantus, Al-Khwarizmi's systematic methods, India's quiet embrace of zero and negative numbers, Viette and Descartes' elegant notation. Each piece, patiently gathered across thousands of years, finally provided exactly the tools Newton and Leibniz needed to describe motion, change, and continuous relationships with newfound precision. And algebra itself, rather than standing still, continued quietly expanding alongside this new discovery. Mathematicians began applying algebraic thinking to increasingly abstract situations, no longer limited to simple numbers or even simple curves, but extending gently into ideas involving infinite series, complex relationships between multiple changing quantities, and increasingly sophisticated systems of equations working together. Picture, if you'd like, a gentle image resting here. A single falling object tracing a smooth curve through the air. Centuries of patient algebraic thought quietly gathered together into new symbols, new methods, finally allowing mathematicians to describe, with remarkable precision, exactly how that object moves through every single instant of its fall. Not just where it starts and where it lands, but the complete, continuous story of its motion in between. This period also saw algebra begin quietly merging with an increasing number of other mathematical fields: probability, mechanics, astronomy, each one borrowing algebraic tools to describe patterns and relationships that had once felt far too complex to capture with any real precision. Algebra was no longer simply a tool for solving isolated equations. It was becoming something closer to a universal language, capable of describing motion, chance, structure, and change, all within the same careful, symbolic framework. Let your thoughts rest here for a while, imagining two quiet studies, an ocean apart, each filled with careful notes and diagrams, two minds working patiently toward remarkably similar truths. In the next part of our story, we'll follow algebra into an even stranger, more abstract chapter, guided by a brilliant, tragic young mathematician whose work, written frantically through a single, desperate night, would quietly reshape the entire future of the subject. Let the quiet studies of Newton and Leibniz fade gently now into the dark behind us. We're traveling forward once more into early 19th century France, toward one of the most quietly tragic and quietly brilliant chapters in this entire long story. This is the story of Évariste Galois, a young man whose life was remarkably short, but whose ideas would reach forward patiently for generations after his death. Picture him first as a restless, brilliant student, easily bored by the slow pace of his formal schooling, already reading advanced mathematical texts on his own, quietly, long before his teachers felt he was ready for them. From an early age, Galois showed a rare, intense gift for mathematics, though his impatience and independent nature often placed him at odds with the more rigid academic world around him. By this point in our story, remember, mathematicians had already learned to solve equations involving an unknown raised to the second, third, and even fourth power, quadratics, cubics, and quartics, through the patient, sometimes dramatic work of mathematicians stretching all the way back to Babylon, and more recently, through figures like Cardano and Ferrari. A natural question quietly lingered in the mathematical world of the time. Could a similar general method be found for equations involving an unknown raised to the fifth power and beyond? Galois approached this question in a way that felt, at the time, remarkably unusual. Rather than searching directly for a formula, the way earlier mathematicians had, he began asking a deeper, more structural question. He wanted to understand the underlying symmetry, the hidden relationships between the solutions of an equation, rather than simply calculating the solutions themselves. In doing so, quietly and almost accidentally, he laid the foundation for an entirely new branch of mathematics, now known as group theory, a field that would eventually become central to what mathematicians call abstract algebra. Take a slow, gentle breath here, because this represents one final, profound shift in our long story. Until this point, algebra had almost always been about solving for specific unknown quantities, numbers waiting patiently to be found. Galois' work quietly redirected algebra towards something more abstract entirely, the study of structure itself, the patterns and relationships that connect mathematical objects together, regardless of the particular numbers involved. Galois showed, through careful, brilliant reasoning, that no general formula could exist for solving equations involving a fifth power or higher, at least not one built from the simple combinations of addition, subtraction, multiplication, division, and roots that earlier mathematicians had relied on. It was, in its own quiet way, a profound and unexpected answer. Not every mathematical problem, it turned out, could be solved through the methods that had worked so reliably for thousands of years before. But the true significance of his work reached far beyond that single answer. In developing the reasoning needed to reach this conclusion, Galois created an entirely new mathematical language for describing symmetry and structure, one that would quietly ripple outward for the next 2 centuries, eventually influencing fields as varied as physics, chemistry, cryptography, and computer science. And yet, tragically, gently, Galois would not live to see any of this recognized. His personal life was marked by repeated setbacks, rejected university applications, political turmoil during a particularly unstable period in French history, and a series of misunderstandings that left much of his mathematical work misunderstood or overlooked by the academic establishment of his time. In the spring of 1832, at just 20 years old, Galois became involved in a dispute that led to a duel, the exact circumstances of which remain, even now, quietly uncertain, tangled somewhere between politics, personal conflict, and matters of the heart. The night before the duel, believing he might not survive until morning, Galois stayed awake for hours, writing frantically by candlelight, trying to capture as much of his mathematical thinking as possible, aware that if he died, his ideas might disappear along with him. Picture that quiet, urgent scene for a moment, gently, without rushing past it. A young man, barely into adulthood, working through the night, not out of academic obligation, but out of a desperate hope that his ideas might somehow survive him. Scribbled in the margins of his papers, alongside dense mathematical reasoning, are said to be small human notes, moments of doubt, and phrases reflecting the emotional weight of that long, uncertain night. The duel took place the next morning. Galois was shot and died the following day, on the 31st of May, 1832. He was 20 years old. It's a quiet, heavy thing to sit with, isn't it? Especially here, in the gentle stillness of a story meant to ease you towards sleep. So much brilliance, cut short so early, leaving behind pages of dense, hurried mathematics that few people at the time fully understood. It would take more than a decade after his death before other mathematicians, studying his papers carefully, patiently, began to fully grasp the depth of what Galois had actually discovered. Slowly, his ideas were absorbed into the wider mathematical world, quietly reshaping algebra into something far more abstract, far more structural than anything the Babylonians or Egyptians, or even Descartes and Newton, could have imagined. There's a gentle, important truth resting within this particular part of our story. Mathematics has never simply been the product of comfortable, secure lives. It has been carried forward by people facing real struggles, real uncertainty, sometimes even facing their own final hours, and still, quietly, choosing to write, to think, to try to leave something meaningful behind for whoever might come along afterward. Let your thoughts rest gently here for a while, imagining a candle slowly burning low, pages filled with hurried, brilliant handwriting, a young mind reaching desperately toward the future he wouldn't get to see. In the final part of our story tonight, we'll follow algebra into the modern era, gathering together everything we've journeyed through, and gently closing this long, patient story the way all good stories and all good nights eventually come to rest. Let the candle from Galois' final night burn softly down now, gently into the quiet dark. We're arriving at last at the final part of our long journey together tonight, drifting forward into the modern era, where algebra finally settles into the vast, abstract shape it holds today. After Galois, mathematicians slowly began to realize that algebra could describe far more than numbers, or even the unknown quantities we've followed so patiently throughout this story. It could describe structure itself, the quiet rules governing how objects relate to and combine with one another, regardless of what those particular objects actually were. Picture gently what this shift really meant. A mathematician no longer needed to be working with ordinary numbers at all. They might study a set of symmetries, the different ways a shape could be rotated or reflected while still looking the same. They might study permutations, the different ways a collection of objects could be rearranged. They might study entirely abstract systems built from careful, chosen rules with no obvious connection to counting or measuring anything in the physical world at all. Throughout the late 19th and early 20th centuries, mathematicians slowly, patiently built upon Galois' foundation, developing what we now simply call abstract algebra, an umbrella covering fields with names like group theory, ring theory, and field theory. Each of these fields studies its own particular kind of structure, its own particular set of rules, but all of them trace their quiet lineage back to that same fundamental shift Galois first glimpsed, late one candlelit night before his final, tragic morning. It's worth pausing here, gently, to notice how far we've traveled since the very beginning of our story. We started with Babylonian scribes, pressing careful marks into damp clay, solving practical problems about grain and land and debt. We've arrived, many centuries later, at mathematicians studying abstract structures with no obvious connection to daily life whatsoever. Structures so refined, so general, that they can describe patterns hiding within nearly anything. Numbers, shapes, symmetries, even the quiet architecture of modern computer science and cryptography. And yet, despite how abstract algebra eventually became, its roots never really left behind that original, patient spirit we found at the very start of this journey. Remember, algebra began not from idle curiosity, but from real, human necessity. Dividing land fairly, calculating interest, understanding how one quantity changes in relation to another. Even now, in its most abstract modern form, algebra still, quietly, at its core, remains a language for describing relationships, how different things connect, combine, and transform in relation to one another. Modern algebra now touches nearly every corner of daily life, often invisibly, quietly working behind the scenes without most of us ever noticing. The encryption protecting your private messages online relies on algebraic structures built from number theory. The search engines, quietly sorting through billions of pages, rely on complex algebraic and statistical methods. Even the gentle curve of a suspension bridge or the careful trajectory of a spacecraft depends on centuries of patient algebraic thought, stretching all the way back to those early Babylonian scribes, quietly working by lamplight thousands of years ago. There's a particular kind of comfort in resting on that thought as you drift towards sleep tonight. Algebra was never really about X's and Y's, formulas memorized reluctantly for a school exam. It was always about something far more human than that. Patient people across thousands of years and dozens of civilizations, quietly trying to understand the world around them a little more clearly, trying to find the unknown, trying to see the hidden structure connecting one thing gently to another. Think back for a moment, gently, across everything we've traveled through together tonight. Babylonian scribes, solving practical problems with nothing but careful, patient language. Egyptian officials, calculating grain and taxes along the quiet banks of the Nile. Greek philosophers, translating numbers into shapes and lines. Diophantus, quietly nudging algebra toward abbreviation and symbol. Indian mathematicians, gently welcoming zero and negative numbers into the world of legitimate numbers. Al-Khwarizmi, weaving centuries of scattered knowledge into one careful, systematic method and giving algebra the very name we still use. Fibonacci, carrying new numerals gently into Europe. Tartaglia and Cardano, racing through candlelit nights toward the cubic equation. Viette and Descartes, finally giving algebra its clean, familiar symbols. Newton and Leibniz, stretching algebra into the continuous motion of the physical world. And finally, Galois, reaching in his final hours toward an entirely new, abstract understanding of structure itself. None of them worked entirely alone, even when it felt that way. Each one quietly inherited the patient work of those who came before, and each one quietly passed something forward to those who would come after, most of them never fully realizing how far their small, careful contribution would eventually travel. And that thread continues even now, quietly, gently, all the way to tonight, to you, resting here, listening to this long, unfinished story. Algebra isn't a closed book, completed thousands of years ago and simply handed down unchanged. It's still being written, still being gently expanded by mathematicians working quietly, right now, somewhere in the world, on problems we don't yet have names for. You don't need to solve a single equation tonight. You don't need to remember a single formula. All that matters, gently, is this. Somewhere in the quiet architecture of your own thinking, whenever you notice a pattern, whenever you wonder how one thing relates to another, whenever you quietly reason your way from what you know toward what you don't yet understand, you're taking part in the very same patient tradition that stretches all the way back to those careful Babylonian scribes, working by lamplight nearly 4,000 years ago. Let your thoughts rest here now, fully, gently, at the end of this long, unfolding story. There's nothing more you need to think about tonight, just the quiet, comforting knowledge that some ideas take thousands of years to fully unfold, patiently, one careful mind at a time. The same slow, patient way sleep itself is gently unfolding for you right now. Rest well.